So if you have the pattern, there are approximate formulas that give you a clue about the directivity of the antenna. And knowing the angles, half power beamwidth in horizontal and vertical direction, you can tell the directivity of the antenna. Let's say if we have 10 degrees in horizontal and 10 degrees in vertical, what will be the directivity of the antenna? 412 times. Yeah, right. Ten horizontal, 10 vertical.
vertical. Okay.
And if we have a planar antenna array, like you say, because of the distribution, we reduce slightly the gain number. We get 32,400 over the beamwidth of the array. If the beamwidth is 1 degree, we have 32,000 more directive than isotropic. And then the next concept, antenna gain.
One question. Physically, how do we make the antenna directive? Do we add a wafer, like a structure that would reflect the wave from the source, or do we play around with the nature of the source, like the dipole monopole kind of?
Both. We use both approaches. We play with the source and we put reflector. And you will see. So what is the gain? The gain of the antenna is exactly the same as directivity, but we subtract the losses. So directivity of the antenna is calculated for the power that already departed the antenna. And the gain is the same, but on antenna inputs. And we have any type of losses, which could be due to finite conductivity of the conductors, a reflection from the input port, or dielectric losses inside the antenna. They are counted into the gain number. So which of these two is more relevant to the real life?
Which relevant to the real life?
Yes.
Which two?
Which
Between gain and directivity.
Again?
Gain because it counts for the losses.
So what we measure?
Yes.
And despite that we use the word gain, this is not a gain of an amplifier. Here we just redistribute the power from one direction to another and compare it, the result with isotropic radiator. So this is the gain compared to isotropic antenna, not the gain itself. What? Not doesn't do business for you?
No.
You expected that.
So gain here means what? Amplification.
Compare it to isotropic radiator, but not a physical amplification.
Why not physical?
You don't add more to that signal. You just get it from here and put it to there. It's like if you have
Distribution.
5 lefts and you get it from one pocket and put it to the other, you will see 5 lefts gain into the value of that pocket. But in general,
there is no
gain. So this is the same here. You see improvement against isotropic radiator. But,
Okay.
And then you will ask, why don't we use something else? Unfortunately, there is nothing else what we can do. We can use only isotropic radiator or something more directive. But that's all options. We don't have anything else that can physically
We have any benefit to the whole picture.
Exactly. Are we clear now with the concept of antenna? Now, maybe we have to say the words that we measure the gain. It's decibels against isotropic radiator. And the unit of merit is dBi, decibels, compared to isotropic radiator. Not physical gain itself. Amplifier, it has ability to increase the signal. You put 1 volt in the input and you get 10 volts on the output. Antenna is not like that. You will see increase in the signal, but if you...
But due to the characteristic of the receiver.
Yes. If you replace it with isotropic radiator, you will see the increase, but it's not a physical increase. You don't have more signals coming from the space or get amplified. That's good to know.
Yeah. Значи същото.
Other parameters of the antenna, the bandwidth. Antenna bandwidth. This is important to know that with respect to other types of devices like filter or amplifier, here the bandwidth is something more complicated thing. In antennas, the bandwidth is the frequency band where most of the parameters like gain, pattern direction, polarization, return loss stay the same or within acceptable limits. In amplifiers, filters, it's easy. You just say, where we see a drop of 3 dBs, this is the enter the bandpass of the filter. Here, there are more things to put in the consideration, yes. Maybe if the gain is constant but polarization rotates, antenna is not usable. We cannot say we can use it for this particular frequency. Or the pattern is constant but actually return loss is high, then we cannot use it.
Yeah.
So more things we have to consider first. Second, for broadband antennas, let's say from 1 to 6 gigahertz, like ultra wideband antenna, the frequency bandwidth is take as a fraction, like 6 to 1, 5 to 1. Say antenna is pretty broadband. If the antenna is narrowband, the bandwidth is given as percentage of central frequency. And the top engineers don't use the average value, but the mean square root. Yes, mean square. Root mean square. This is more natural to the reality than the average. Okay. So this is the bandwidth. And now we come to the question that was raised this morning. What is polarization? Polarization of wave is the figure that propagating tip describes in the space. But what makes this tip to make a figure in the space?
source.
itself is some sort of a fluctuation in space.
It's the source that makes
The source makes it, and the source is antenna. So if we make antenna to force the field to do something, it will do something.
Yeah, okay.
And how do we force it? Easy.
shape.
Yes, shape. Configuration. Here we have a dipole, and we have another dipole here. And we fed this one, and this one with zero phase. What shape will be the transmitted signal? If we have zero phase difference, it will have, let's say, this shape. What will happen if we switch the phase to 180? Nothing. It will just reverse. And what will be if we put 90 degrees difference between these two?
The direction of the signal will turn 90 degrees.
It will start to make circles, and that's how circular polarization is introduced.
And what if it is on 90 degrees or 180 degrees?
Hmm?
What if it's another angle? Not 90 degrees, not 180 degrees.
It will have an arbitrary tilt relating to the. It will still form an ellipse like that with tilt towards something. So perfect circle is not easy to make. You need perfectly 90 degrees phase difference and perfectly equal split of power between these two sources. This is the two conditions to make a circular polarization. In any other case, you get elliptical, which is the most common case, and some of the other extremity is the linear. When you have killed one of the sources, or you have 0 or 180 phase difference and equal power. So elliptical is most common, with the two extremes, linear and circular.
If someone says that the light isn't polarized, what would you do? If someone says that the light isn't polarized,
It means it has arbitrary.
One time like this, next time like this, next time like this, next time like this. So it's like all probabilities of angles are possible.
And your receptor recepts light with arbitrary polarization.
so for example, our sun, what sort of light does it emit?
No.
So the sun emits no
Arbitrary, yes. Actually, all polarization.
polarizations, yeah, right.
And if you pass it to a polarization filter, you filter out some of the components. That's why anti-glare glasses, they have a polarization filter. And if you take a look on the reflection, it gets killed because the reflected is somewhat
Reflected light is somewhat polarized. What do we gain from the polarization in the sense of receiver and transmitter? Like, is it like, do we transmit data in some, like in a phase, or?
absolutely on the same frequency. You can transmit completely different channel on the orthogonal polarization.
Okay, so you basically double
Double the communication channel.
the communication channel. That's why you use polarized instead of
Exactly.
arbitrary.
But only 2 times. or
Only is not a small thing, you know, it's
Take it if you can.
100 lefts against 200 lefts, so only if you go to shop and say, oh, this is only twice more expensive. Only. And this is how these two external cases are: linear, circular, and the general is elliptical.
So the signal with the exact same frequency amplitude but different phase would not interfere with each other. Okay? Signals with the exact same frequency, amplitude but different phase, different polarization would not interfere with each other.
No, this is fundamental concept. Signals can pass one through another and they don't interfere.
But how this is possible? When there are two
Different
energies in space
Yes, but
that
that's
waves
how
that travel at the same time in one
It's
single
actually
space.
not the same energy. Because
But it's in the same
polarization
medium.
is part of the energy. So it's like the electron states in quantum mechanics. The spin up and spin down are considered different energies, so they don't overlap, they don't interfere.
But physically they're in the same space.
I think my
That's fine.
explanation would be the principle of
If they're in
superposition.
the
Don't
same,
they-
yes, exactly. If they're in the same space but they're different frequency, they don't interfere, right?
If you have two vectors, you usually add them up, right? And that's how you describe interference. But what in this case, one of the vectors is in one plane and the other one is in a plane orthogonal to this one. So
No,
that's my
this is to receive them. I think how they don't interfere when they're in the same medium at the same place.
they're transmitted during the transmission itself.
No, when the two waves interact, they contact each other physically in space. Why they don't interfere?
that's how the space work.
But why?
Why
The work
I
is
don't
work.
know.
Interference
I will get double
they're the
price
same
if I know, but
frequency
I
and
don't know.
expected to be the same energy. So when they're different polarization, my understanding is like in quantum mechanical states, different energies are different states. So the same electron transition from this state to this state will give you the same wave. But if it's spin up, this state gets split in two. So there's a small difference in the two energies where one is like the level gets split into two levels when one is spin down, the other one is spin up. So this is essentially two different states and two different energies, so they don't interfere.
Well, they may interfere, but we are not able to detect this interference.
Very small.
This is the, I think, the explanation.
You know, if you imagine a space-time fabric and one polarization pull it in this direction, the other pull it in this direction, we can either see the one or the other, but not two at the same time.
Yeah, probably this is.
Maybe, but
Yeah.
if I say this in public,
Yeah.
and how do we characterize the circular polarization? With the ratio between major and minor axes. It is called axial ratio. And the closer to 1, to unity, the better polarization is. And I heard that a lot of things with the telescope are measuring the axial ratio of the source, the star or the galaxy. It gives some information,
Yes. It
but
gives.
nobody knows what actually stands behind. That's what they told me, radio astronomers, very important, but we don't know why. And the problem also is the waves are passing through the atmosphere, ionosphere. And passing through the ionosphere, it gets impacted due to the polarization. Yes. And this ruins the quality of the measurement.
Yeah.
So you need to wait for very calm ionosphere to make a valid measurement.
Atmosphere is the best friend of humanity and the worst enemy of astronomers.
Yes, that's why if we build telescopes that are not impacted by the polarization, good, like above 1 gigahertz or actually 3 gigahertz and 4 gigahertz, a bit 6 gigahertz for sure, or find a way to calibrate the telescope to counteract the.
I just want to say something that I just checked. It is absolutely possible for light of different wavelengths to interfere, light waves with different wavelengths to interfere, just they don't form a constant interference pattern, but they absolutely do.
Strictly, what people say not possible. If somebody proves that wrong, get the Nobel Prize. To me, very likely, as the colleague said, very likely it interferes, but we cannot measure that.
Because we don't have invented the
Practically
new
doesn't.
detector.
Like we said, if we can't measure it, we don't care about it.
Yes. So, in theory, no, they're completely different, invariant, but in practice, there are things more behind that. They are not written in the big books.
Yeah.
Okay,
Like one of the most prominent Bulgarian scientists that used to work in the United States detected that in a moment of explosion, electromagnetic wave is excited and propagates. So you can detect explosion by observing the EM field. Why this happens so often in chemical reactions doesn't produce EM waves? Is it because it creates a shock into the space-time, or something else that we don't know? We don't know. If I read Balani's book on antennas, which is 2,000 pages, there is no single line about it. Nor in the physics books. You know, they say completely two waves pass one each other without interference. Great, you know, that's what I have examined to get a position here at the university.
Yeah.
Good questions that we don't have
Answers yet.
effective area. Oh, nice, very nice. Now you will grasp the concept of antennas. Imagine we have transmitter here, and I put powers to the transmitter antenna. This power, EM power, gets radiated and propagates, and reaching here will create a power flux density. Right? How we do calculate the power flux density? That's how. P transmit divided the 4 pi r squared. That's the area of the sphere that encircles the receiver. Why so? Very simple. We have a source here that transmits, and our sphere with that radius, the area of that sphere is 4 pi r squared. So this power is distributed over the sphere, and will give us the power flux density. And the only thing that we have to add this to the equation is what?
Was gain.
Gain of the transmit antenna. Since this antenna is directional, when we multiply this power flux density of isotropic radiator to the gain of the transmit antenna, for this particular direction, we will have this power flux density clear?
But this is of the transmitter,
Yes.
not of the
For
receiver.
instance, we have the receiver receives. We have 10 watts, and we have sphere with radius of 10 meters. We're 10 meters away from the source. So what will be the power flux density? It will be 10 watts or 4 pi 10 meters squared. Clear? Clear. And we have 20 times gain of the antenna. Then we have to multiply this number to 20, and we get 20 times 10 watts over 4 pi 10 meters squared sphere. And what if we put here a receiver with 1 meter area that it can extract the energy from? What will be the total received power? Exactly. It will be the
ST
ST hour,
gain of
not
the
hour,
no,
not hour. It will be ST times
gain of the
area,
receiver.
times area, reception area.
Yeah.
Flux is power over area, so multiplied by the area.
Yes.
to get the power.
And the beauty of this is that for each antenna we know what is the effective area. The effective area is area of isotropic radiator, which is lambda squared over 4 pi, times the gain of the receive antenna. And this will tell us what is the virtual area from which the receiver gets the power from the space.
Question.
Yes?
Always in the transmitter there is a so-called reflector power.
Yes, but we neglected here,
You
just
will get here.
for the sake of
Yeah,
simplicity.
yeah.
So now you have the concept of how the energy is transmitted through the space.
Okay, and loss of power in the space propagation.
It's to gain.
Here,
Okay.
the larger
Divide
the
it,
distance,
yeah.
the larger the
Would-
sphere.
Yeah. Radius.
Beauty, huh? And here is what we just said. The first invented this equation is called Harald Fries, a Dutch engineer that immigrated to the United States, and together with one Russian immigrant called Shelkunov, Sergei Shelkunov, they developed this concept called Fries transmission equation. So if we have transmitter, receiver, two antennas, the distance between them, and the wavelength, we can easily calculate how much power we transmit and how much power we receive from the receive side. And everything, all communication equipment in our world, and all radio astronomy equipment is governed by this equation.
What is D2 VR? What are those?
Yes. dt and dr are the directivity of the transmit and receive antenna. Etas are their efficiency. So basically, this is the
At the time D is the G, isn't it?
yes, exactly. At the t, the t is the gain of the transmit antenna, gain of the receive antenna. Lambda is the wavelength. 4 pi r is the distance. Everything in our world working on a free space propagation is governed by this. If we have different media, like a waveguide, we will have no loss or no loss of so much times. Which kind of leads me to believe that if we create a way to keep the waves propagating in a some space-time tunnel,
Like optical networking.
kind of, but not
Wait,
not with physical medium, but with some space-time medium to keep the wave in place. We will have lossless energy transmission,
Perfect lasers.
kind of. Laser also is governed by this. But if we rely only on free space propagation based on interference and Huygens principle at each point of the waveform,
Definitely not very effective.
we have to live with this square law loss. And to make things perfectly clear, gentlemen, please solve